Hello everyone and welcome to our presentation on the model we've developed using Hugging Face Library Transformer. I am Razat and along with my friend Zeke, we will be showcasing our resume screening model.
The objective is to develop a robust resume screening model using BERT for classifying resumes into different job categories. Motivation and team goals. Why this project? We're addressing challenges in resume screening and improving accuracy to match candidates to job descriptions. Team goals is to refine and better use this model for real-world applications and also balance projects tasks efficiently.
So our plan was to develop a simple resume categorization model by using the pre-trained distillbird, and the steps included in it was data pre-processing, fine-tuning the model, and the finally deploying the model in the real world.
Project challenges. So changes in scope. Shift focus to include skill extraction and job matching. Remove resume ranking completely due to complexity of model. Challenges faced. Managing imbalanced data and adjusting architectures to meet new requirements.
So let's dive into the development of our model. Initially, we planned to use pre-trained distillbird. However, as our research progressed, we realized that a more customized approach was needed to effectively address our goals. So our final implementation involved fine-tuning BERT with a custom architecture tailored for skill extraction. We enhanced our data pre-processing by utilizing BERT's tokenizer and developed custom cleaning functions to improve accuracy. Our exploration extended to NLP techniques for entity and relation extraction, including named entity recognition, also known as NER, and dependency parsing. These methods were crucial for accurately extracting skills and qualifications from resumes and matching them with the job descriptions. Let's look at the model architecture. It consists of different layers and they work together to perform an output. The model starts with the input layer where the text is tokenized into input IDs. This goes with attention marks, which helps the model to focus on the actual content by ignoring the padding. Next, we have BERT embeddings where tokens are converted into dense vectors. This layer combines word embeddings, position embeddings, and token type embeddings. Layer normalization and dropout are applied to stabilize and regularize the embeddings. The next layer is BERT encoder, which is the core component and is made up of 12 layers. Each layer includes self-attention, which determines the importance of words, and intermediate layer that expands dimension from 768 to 3072, and also an output layer that reduces them back to 762, applying layer norm and dropout. After the encoder, the pooler layer extracts a fixed size representation from the CLS token using a dense layer with 10 activation. This summary vector is key for the downstream tasks. Finally, we pass through a dropout layer, then a classifier that maps the vector to 25 classes. The output layer produces the final predictions for these classes. Before model implementation, we did EDA to understand the dataset. This helped us to detect issues with the class imbalance. We used pie chart, bar chart, and word cloud to do the data analysis. In the bar chart, you can see that the number of Java developer is more. However, in the pie chart, it shows the data science has the more amount of data. This is the class imbalance we need to fix during the pre-processing phase. We also generated the word cloud to visualize the most common words in resumes. This helped us to quickly identify the frequently occurring terms such as keywords and common words like experience, skills, etc.
Model refinement. Parameters tuning. Learning rate fixed to 2e -5 for optimal performance. Batch size. This sits at a level that is changeable but optimized for the best performance. Number of epochs. Based on the verified results, it has grown to 7. Data augmentation. Oversampling techniques to tackle class imbalance, improved capabilities of models to generalize and to monetize classes, fine tuning of the BERT for better fine tuning we're done in case to help improve accuracy. We put a lower performance class in terms of prediction. Training. Training purposes. The data is split into training, verification, and test set splits. EBNOCs have been limited up to 7, but earlier stopping since then. Evaluation measures. Accuracy sits more than 90%. The confusion matrix analysis involves misclass information, specializing within several job applications. A classification report of recalls, F1 score, and final making the model making the model work generally well with new data, and room for improvement for handling overlap job requirements.
One of the key challenges we faced was the computational load required for the training BERT model, which was a GPU environment. We also encountered data quality issues, particularly in standardizing resumes for feature extraction. However, through collaboration, we fine-tuned the model and overcame these troubles, which strengthened our teamwork and technical problem-solving skills. In the end, we achieved our goal of creating a high accuracy resume classification model with more than 90% accuracy score. Not only did it categorize resumes effectively, but it also extracted skills relevant to real world recruitment applications. For future improvements, we plan to further address class imbalances and enhance the model ability to differentiate between similar job roles. To conclude, this project was a journey from basic machine learning pipeline to a sophisticated NLP model. It highlighted the importance of adaptability, collaboration, and advanced NLP techniques in solving real-world problems. We believe our work demonstrates the potential of BERT in automating and improving resume screening processes, and we're excited to see how it can be further developed. Thank you.